Okay, it's Brian. We're back for another installment, and this is the first one where I'm really going to start talking about content. And we're going to start looking at one-dimensional motion or motion along a line. And this is the introductory slide here. And I want to make this clear. You need to have kind of a picture in your mind as to what's happening with the motion. And then we have to represent it. And typically I want to draw some sort of a picture to help us wrap our mind around the motion and different phases of the motion and what's happening. And only then do we do equations. I'm just going to warn you right now, a lot of you have a tendency to want to shortcut from the story to the equations, but you need to make a detour first to the pictures. And we're going to spend a lot of time thinking about the pictures. And that will just help you wrap your mind around what's happening with the problem, and then you come here. And that's really, really important. As a general rule, you folks like to just jump right into equations and start putting numbers into equations. And if you do that, down that road lies madness. Do not do it. And so we're going to spend lots of time thinking about the pictures. And that's sort of a general rule in the class to come. And here's a picture of motion. And this is a picture, and it's what we call a motion diagram. So with a motion diagram, we have a series of dots that represent the position of an object, in this case a person on a bicycle. And if you look at the distance between successive dots like this one and this one, here's the distance between them. That represents the distance that the bike traveled in a certain time interval, and let's call that delta x. And then if I look at a later time, say at these 2 points right here, and I look at the distance traveled between those 2 points, the distance is bigger. And so the speed is increasing, and you know this intuitively just by looking at it, but we'll have an equation where we're going to use to calculate speeds, and the speed, or the velocity, is just equal to the distance traveled divided by the time interval. So for instance, you would have speeds in miles per hour, a distance divided by a time. In this class, we're going to tend to use meters and seconds, and so we'll have speeds in meters per second. And looking at this picture, looking at this motion diagram, you can see that what's happening is the bike is steadily speeding up as Heather is cycling to the right. Now, if we're going to represent motion, we need some way to represent measured distances from. Okay, and so we need to have some sort of a coordinate system, and I've used as an example the yard lines on a football field. And so I've got the 50-yard line and the 40-yard line, et cetera, and we've got a definite kind of like point where we start to make measurements from, and we measure everything from there. So we've got a coordinate system. That's kind of a crucial thing for making measurements. Now let's look at some conventions for coordinate systems. Okay, so I have an object, and its initial position is here, so we have a motion diagram describing the motion, and this is uniform motion. If you look at the successive positions between these dots, they're all the same. This is something which is moving at basically a constant speed. Okay, we're going to call the initial position xi, that's our symbol for it, and it's at a time, I'm going to call that time ti, and where possible, I'm going to just let xi be equal to 0 and ti be equal to 0. That's just a useful convention. We can set the initial time, and we can set the 0 of our position and the 0 of our time anywhere we want. So let's just take it at the start of a problem. That tends to make things easier for us. Now, if I have my origin here and my initial position, I've let that be at x is equal to 0. In this case, the object is clearly moving to the right. And when something moves to the right, it's moving to positions where the x value that represents the position is greater than 0. If it moves to the left, we're going to say x is less than 0. And we do the same thing for the y-axis. If we have vertical motion, if something's above the origin, we're going to say that corresponds to y greater than 0. If something's below the origin, we'll say that corresponds to y less than 0. Except here's the thing. When we do vertical motion, rather than picking the value for my 0 position, I'm just going to say 0 position is at the surface of the earth, okay? And so y is always positive. And it kind of makes sense. I mean, it's just measuring from the ground, and so any value of y is going to be up from the ground. And so any position we look at is typically y greater than 0, and that's a good convention for us. Now you can look at these in more detail in the textbook. And if you're watching this during the first week of classes, over the weekend I want you to read chapter 1, or finish reading chapter 1, and read chapter 2. And all these conventions are laid out in some detail in the textbook. Now I want to talk about one thing which the English language doesn't discriminate between, but physics language does. Velocity and speed in the English language are really kind of about the same. If I say I'm moving at a high velocity or high speed, that means about the same thing. But in physics, it means something extremely different. Speed is just the value. How fast are you going? Velocity is the speed, but also involves the direction. And so our convention is going to be, if something is moving to the right, that's going to be a velocity that's greater than 0. If something's moving to the left, that's a velocity that's less than 0. And the way I know it's a velocity, not just a speed, is I have a subscript x on it. Okay, that's a velocity. So Vx greater than 0, moving to the right. Vx less than 0, moving to the left. And this will correspond to this equation right here that we use to calculate velocities. Velocity is equal to delta x over delta t. So this is the distance that it's moved right here, delta x, in a time interval, delta t. Except the thing is, if it's moving to the left, delta x is less than 0. And if delta x is less than 0, the velocity Vx is going to be less than 0. That's an object moving to the left. If I have an object that's moving to the right, Vx, or delta x, is going to be greater than 0. And so therefore Vx will be greater than 0, as we've seen. That's our convention for velocities. We'll do the same thing for vertical velocities. If an object is moving upward, that corresponds to a positive velocity. If an object is moving downward, that corresponds to a negative velocity. Now, if it's the speed is just the magnitude. It's the number. On your car, you have a speedometer. And if it says you're going at 40 miles per hour, it doesn't say you're going 40 miles per hour to the west or to the east or to the north or the south. It just tells you how fast you're going. That's what we mean by speed. Now, in this class, we're typically going to compute speeds in meters per second because the basic unit of distance we use is the meter. The basic unit of time is the second. So velocities, or speeds, and if it's speed, there's no subscript x. V is just equal to delta x over delta t, but it's an absolute value. It's always a positive number. Okay, the speeds are going to be a distance divided by a time. For our basic units of distance is meters, a basic unit of time is seconds. I'm going to do meters per second. And so that you can compare numbers when you get done, 1 meter per second is about 2 miles per hour. So if you're walking at a very, very chill pace, okay, the speed that you're walking at, you take one stride and it's about 1 meter, and you take one stride about every 1 second if you're walking at a very, very gentle pace. And by the way, one stride, I mean 2 steps. That's one complete stride. Okay, 1 meter is about 1 stride, and you do one of those about every second. If you're walking at a very, very mellow speed, that's about 1 meter per second, or about 2 miles per hour. Now the next quantity I want to look at is acceleration. And acceleration is a change in velocity divided by time. It's a rate of change of velocity. Okay? Velocity is a rate of change of position. So if I have vertical velocity, just delta y over delta t, how much is your position changing in every time interval? Acceleration is the change in velocity per unit time interval. How much is your velocity changing in a certain time interval? And if you look at this person falling off a platform and look at the position, the successive positions get farther and farther apart. And so that tells me that delta y in each interval of time is getting bigger. So as a consequence, the vertical speed is getting bigger. I'm not worried about signs right now. I'm just doing speeds. Because it's just the person is moving farther in every interval of time. And that means the velocity is changing. If the velocity is changing, that means there is an acceleration. And the units for acceleration are this. Okay? Acceleration is equal to a change in velocity divided by a time interval. Well, a change of velocity is in meters per second, and time is in seconds. And so the units of acceleration are meters per second, or meters per second squared. But really, I like to think about them as this way: it's meters per second. What is the acceleration? It's a certain number of meters per second. How much is your velocity changing in every time interval? Now let's look at the sign of acceleration, okay? So acceleration is defined as this. It's the change in velocity divided by an interval of time. But I want to look at the case of someone who is falling. Okay, so here's the person originally, and then they're here, and then they're here, and then they're here. You can see in every interval of time they're going a little bit farther. I'm going to represent their travel by doing velocity vectors. And the velocity vectors are pointing downward because the person is moving downward, but the size of the vectors is getting bigger. So what that tells me is the person is falling, and they're falling at a higher and higher speed. But let's suppose we write it as velocities, which have signs. Well, since the velocity is downward, it's a negative number. And suppose my original velocity was -10. On the next interval of time, maybe it's -20. It's bigger. Next one, maybe it's -30. The magnitude is bigger. Next interval of time, maybe it's -40. And actually, if it was units of seconds, those would be the numbers that we would get, because if you're in free fall, as this person is, the velocity is going to change by about -10 meters per second every second. So it goes from -10 to -20, -20 to -30, the change is -10, -30 to -40, the change is -10. And so this velocity is changing by about -10 meters per second every second. And so we'd end up with an acceleration of -10 meters per second, or -10 meters per second squared. And that is approximately the acceleration of free fall. But the interesting thing is the acceleration is negative, and the acceleration is negative because the person is moving downward and is moving downward at a higher and higher speed. So the velocity is basically in the hole. It's negative, and it's getting negativer, and that's a bad change. If you're $10 in debt, and then you're $20 in debt, and $30 in debt, and then $40 in debt, you are losing money. That is a negative change. Now let's look at a couple of cases of motion. And the first one that we're going to look at is so-called uniform motion, or motion with constant velocity. And here's a motion diagram for an object moving at constant velocity. It's moving to the right, and it moves the same amount every time interval. So my velocity arrows are all the same size. The velocity is constant. It's moving to the right at a steady rate. If I graph it, the position is just getting steadily bigger because the object is moving to the right. Now that we have some pictures, we can think about it in terms of equations, and the most basic form of the equation is this one. The change in position is just equal to the time interval times the velocity. And if it's a positive velocity, delta x gets bigger. If it's a negative velocity, delta x is getting smaller. The full featured version of the equation looks like this. The final position is equal to the initial position plus the velocity times the time interval. And this equation only applies when you have uniform motion, when the velocity is constant. So this equation is true if the motion is uniform. If the motion is not uniform, you can't use it. This is one type of motion which we're going to look at, and we're going to model motion as either uniform motion, or another type of motion we have is this. Motion with constant acceleration. Now, if I have motion with constant acceleration, what that means is the velocity is steadily changing. And in this case, I've drawn velocity steadily increasing. If that's true, the rate of change of position increases. And so as a consequence, my position graph is going to look like a parabola. And we've seen some motion diagrams of motion with constant acceleration. For instance, the person falling from the platform, the motion diagram just looks like this. In every second, I have a greater distance traveled. And free fall, as the person falling from the platform, is an example of motion with constant acceleration. And for motion with constant acceleration, we have these three relationships right here. So if you have determined that you can model the motion as motion with constant acceleration, you can use these relationships. If it is not constant acceleration, you cannot. And which one you use kind of depends on what you have and what you want to know. And we're going to talk about that when we think about solving problems. Now, I want you to read the textbook, and I want you to read it in its entirety and look through all the different pieces. But if you're trying to find specific pieces of information for particular types of things in the textbook, we have these things called synthesis boxes. And a synthesis box is a summary of all the key properties. So don't just jump to the synthesis box and just read that. Read the text, and then it sums up everything you need to know about motion. And it says we've got two different kinds of motion. We get uniform motion. We have motion with constant acceleration. So decide which bucket to put the motion in. Is it this one? Or is it this one? That'll give you some pictures to be thinking about as you're doing your motion, and also give you some equations to work with, okay? So the synthesis box is a great place to turn when you're solving problems, and it will put all of the relationships and all of the details about the relationships in one handy place. And this box will be very useful for you. I want you to think about it. And it will also be on the study sheet that I will give you to have at hand when you're taking the test, because when you're solving motion problems, this will be very useful information to have. And with that, we'll wrap it up for today. And then next week, what we're going to talk about is this. We're going to talk about modeling motion. So if you see an object in motion and you're worried, how can I mathematically treat it? The first thing is we have to have some sort of a model. Are we going to model this as motion with constant velocity, constant acceleration? Those are two basic types of motion. And with that in hand, what types of things can we calculate? That is what we'll talk about in week 2.